Right, so I uploaded yesterday homework 3. I'm not sure if you guys saw it. Oh, really?
No, well, you probably I just didn't
forgot
check.
to publish.
No, you maybe just didn't check.
It's published?
I saw
The quiz is two. Quiz 2 is published. Okay, maybe homework 3. I'm gonna check if it's published or not, but I'm gonna double check.
Yeah.
And it's gonna be due on Tuesday. It's a few, like 3 problems on the double integration method and the conjugate mean. All right. Okay, and I have quiz 2 uploaded yesterday, so it's gonna be available until the end of the day. It's gonna be on cable and arches. So just make sure to revise the concept very well, and then take the quiz, 30 minutes. Try to make sure 5 minutes to upload the quiz, like to take a picture or scan it and upload it. I didn't grade anything right now. Maybe I'm gonna grade all the homeworks and the quizzes this week. That's one thing. I know some of you try to take the whole time and then they don't have time to upload the quiz, but try to make 5 minutes. Some of you send me emails about the quiz answers because they couldn't upload it on time. So try to make some time to upload the quiz. All right. So over the last week, we have been talking about the methods to quantify deflection. And I told you guys many times before, deflections is one of the most important characteristics of structure analysis. This is one of our main goals as a structure engineers, that we need to find internal forces and deformation. So that's all what a structure analysis do. All the methods that are out there, energy method, stiffness method, all of them are to find internal forces and find deflections. This week we're gonna spend more time trying to quantify deflection using different methods. So the method that we are gonna work on today, or the series of methods that we're gonna work on, it is called work energy methods. For computing deflection. Let's say computing deformation. Because deflection means deformations means rotation and deflection. Okay, so let's actually revise a little bit. I'm sure that you guys have a little bit of background about work and energy method, either from the dynamics or either from physics. So do you guys know that the energy can be transformed from one way to another? Like, let's say you have a body here, like if you guys remember from the dynamics. If you have a body here and this body is moving with a specific, or you give this body a specific velocity v1, is gonna keep moving, and while it's moving, it's gonna stop at a specific point based on how much energy you are gonna give this body here. So basically, you are trying to transform a kinetic energy, half mv1 squared, to some sort of energy here. But the thing is, the kinetic energy here is gonna be 0, because this energy is gonna be transformed into work. It's gonna work from here to here, and some friction and some stuff. So the energy that you give to the body is gonna be transformed from one shape to another. Same thing between kinetic energy and potential energy. Like, let's say that you are here, and then your body was here, but then you take a ladder or something and you bring your body a little bit up. So once you bring the body above the ground with a specific height, we gave it what's called potential energy. This potential energy is the m, the mass of the body, the g, multiplied by the height. So once you leave this height leave this body fall free from this height, is gonna transform this potential energy to kinetic energy. All right? Maybe it's gonna start by v equal to 0, but then it's gonna have some kind of v and some kind of acceleration. So this is a one way to convert potential energy that this body has into a kinetic energy. Like if I have my body is like there above the ground, this ground is like here, and it's 4 foot above the ground. So if it's 4 foot above the ground, if you leave it, it's gonna go from the high potential energy to the low potential energy until the potential energy is 0. Same thing if you have a spring, like let's say that you have a spring like this. This spring is uncompressed. Uncompressed, that means it doesn't have any energy stored in it. But once you compress this spring and you put a force and you bring this spring to be here, so you put what's called strain energy inside the spring. This strain energy is equal to half K of the spring multiplied by delta S squared, or we can say half K S2 squared minus S1 squared. The unstretched length minus the compression that you have in the spring. So basically, if you let this spring go, it's gonna let this all strain energy go until it reaches to the neutral energy. Okay, so that is the concept of the work and energy principle. Let's see how we can apply this in a structural engineering. Same concept apply when you have a structure. Let's say that you have a beam. This beam is something like this. And you put some loads on this beam. Like before you put the load, there is no energy. There is no energy stored inside the beam, and there is no work has been done on the beam. Because think about it as like this. Our beam is like this. There is no load on the beam. It's zero stored energy and zero work on the beam. But once you put load, the external load B, this load is going to exert work on the beam to have this beam deflected. And this work is transferred into strain energy inside the beam based on the deflection and the internal forces in the beam. So we convert the work done by the external forces into a strain energy inside our internal forces. Like all this structure has many students and many appliances or many equipment in this building. This building, we are exerting work on this building because we are kind of forces, and these forces cause deformation. So you have force multiplied by displacement, it makes work. So this work is stored inside the building as a strain energy. Every element that we are here right now, this slab system, has a strain energy inside because it has bending moment, it has shear, it has normal, and it has deformation happen. So that's called a strain energy. So this is a one way is to find the relationship between the work and the energy so that we can find the deformation in the structural system. But before I start this, I want to make sure that you guys understand the concept of work. Do you guys know what work is? Like if I want to find this body was here, and this body got a specific force F. Let's say the F was something like this. Made that body to move here. So how can I find the work that the force F exerted on this body that make this body move all this distance? S. Do you guys remember that concept?
Isn't it like the integration of like force times displacement?
Exactly. We're gonna get why it's integration, but the thing is, the work is force multiplied by displacement. That's a general concept. If you have a body that is here, and you put force on this body, that makes this body move to get here, so it is the amount of force that you have multiplied by the distance cut by this force. But the thing is, this force has to be in the same line of action and the same direction of the displacement. Like for example, this force as a whole was not responsible of this distance alone. Like just one component of this force was responsible of this distance, which is the horizontal component. Like let's say that this is theta, so this is F cosine theta, because the thing is, there is no way that the vertical component can make a horizontal displacement. So let's put number one, work. So we're gonna talk about work and then we're gonna talk about energy after work. So work is W equal to the force multiplied by delta. However, this delta, like let's say that the force B was able to move this point here. So this is supposed to be delta. They have to be in the same direction. However, we're going to come to the integration. The thing is, what is if the force is variable with delta? Like every time this force keep increasing, or the delta is not a straight line or something. That's why we sometimes write this relationship as the integration of P multiplied by d delta, and this integration from the start point 0 until the end of the distance delta, if B is changing with delta. So we write it in this format. But what if I have this point here and I put a force B that way, but this point didn't move horizontal and it moved downward? Or let's say it moved something like this. The point came here. So I can say that B was only responsible of the horizontal displacement, but the vertical displacement, B didn't do any work in the vertical movement. Because basically, we say that B as a vector, like if I want to write this in a vector format, we say that B as a vector is the dot product of the delta vector. Something like that. And when you have this relationship, that means B vector and the amount of B vector, or the magnitude of B vector, multiplied by the magnitude of delta multiplied by cosine theta, the angle between the force and the displacement. So if the angle between the force and displacement theta is equal to 0, so cosine theta is going to be equal to 1. So basically it's going to be multiplied by delta. But let's say that the point, you have a force that way, but delta is downward. So the angle between them is 90 degrees. So cosine 90 is going to be 0. That means that the work done by B is equal to 0, because there's no way that I push this body that way and it goes downward. If it goes downward, so this force didn't make any work downward. Okay? So work has to be in the same direction of the displacement. If I have my body and I'm pushing that way, so the work has to be like, the force has to be in the same direction of the displacement. Okay? All right, so that's about work done by a force. How about a work done by a moment? The work done by a moment, let's imagine that I have, my point is here, and let's say this is an origin, and I apply a moment on this member, and this member moved. I didn't apply force, I applied moment. And this member moved theta, and this point came here. So the work done by the moment, W, is equal to the moment multiplied by theta. And theta is supposed to be by radian. Or if the moment is changing over, it's not constant, so this is going to be the integration of m d theta and theta from 0 until the final theta. So this is how you quantify the work done by a force or the work done by a moment. Basically, if you have a force and this force is pushing a body, so the work is B multiplied by the displacement. If you have a work done by a moment, so it's going to be the moment multiplied by theta. Okay? All right, does anybody have any question?
The work done by the force of the cosine theta, is that going to be in radians as well, or?
Theta, yeah, no. If the theta isn't cosine, so this has to be degree. It depends on how you have your calculator. You either set the calculator for degree and you put this degree, or you set the calculator to radian and you put this in radian. But it's a cosine 80 degree or cosine 90 degree. We all know that cosine 90 is 0. But if you have your calculator setting for radian, so you have to put 90 as pi over 2. Okay. All right. So that's for work. So how about strain energy? Let's talk about strain energy for a little bit. By the way, all this is external work, like an external force applying on a body, and you can see the displacement. Like this is a force that I can see, like an arm is pushing, or my load, I can see my load is pushing the slab here. So that's an external force. The thing is, the energy, we cannot see it. Or the strain energy is inside the members. We cannot see the moment inside the member. If we want to see it, we need to put sensors, and these sensors measure multiple stuff. Okay, so let's talk about strain energy. 2. All right, let's imagine that we have a bar. A bar means a truss member. and this truss member is connected to the wall, something like this, and you applied an external force B on this truss member be something like this. So what is going to happen to the bar? The bar is going to elongate, right? Because that's a tension. So I assume that this bar have a little bit of elongation, something like this. And we are lucky here that the external deformation is equal to the internal, that we can see it. Like this force grab this, like let's say that this is L, so this is delta L, right? That's what happened. You pull the bar and the bar moved delta L, and actually the force be in the same direction of the delta L. How about the internal forces inside the bar? Let's say it's F. Do you guys know what is the value of F? The normal force, the tension force inside the bar is equal to B, right? Because you pull the bar, B with external force is going to respond with an F, and this F is tension, right? Okay, so the thing is, in a structure analysis, let's actually write the relationship between F and delta. Okay. The relationship between F, the internal forces, and delta can be in a different shapes. Like let's write them. This is 1, this is 2, this is 3. The relationship can be linear, like the thing is you apply the force gradually, like you put 1 ton, 2 ton, 3 ton, and the more force that you put on the member, the more deformation you are gonna get. So you are gonna have something like this. All right, linearly increasing. Let's say that this is F or M. Let's say F for now, and this is delta. If this is M, this is gonna be theta. So you either apply the force gradually or apply the moment gradually. But right now we are talking about bars. Or you have a constant force applying on your element. Like I'm not sure if you guys have been to materials lab and tried to test, do a cylinder test or a cube test for concrete. So you put the load and the load keep increasing over time. So that's it. Or you put one big load and you make it constant and you don't change it. It's gonna be something like this. The load is constant and delta is increasing. So this is F and this is delta. Or sometimes you put a load with a function like this and you keep changing the load with respect to this function. And delta. Alright, so this is different formats of the load. However, in a structure analysis or in our structural system, if our system are linearly elastic, like they are in the elastic zone, this is the behavior. It's something like this. I'm not sure if you guys remember the materials or the steel. The steel is like when you load the steel is something like this. This is the stress, and let's say this is the load B or F, and this is delta. The steel is something like this. As soon as, like, if you have a steel sample and you put it in the lab and try to apply tension, the steel is as soon as linear. And the elastic zone is going to be something like this until it reaches something is called yield zone, and then it goes to a maximum, and then this is the ultimate load that, or we call it the F ultimate. This is F yield, and then it breaks down something like this. That is the steel shape. So if most of our structure, when we design them in the elastic zone. We don't want our structure to come to the yield zone, because if the structure come to the yield zone, it's not gonna come back. Like let's say my structure got hit with an earthquake, and the earthquake made my structural elements, columns, beams, walls, everything, go to this zone. The thing is, if my earthquake is hitting within this zone with a force like this, once the earthquake is gone, the structure is gonna go back to its original place because it's elastic. So you hit and it's gonna go back. But if my structure come to this zone, it's not gonna go back. It's gonna come back here, and you are gonna have a permanent deformation in the structure. It's not gonna come back to its original place. There's a permanent deformation. So your structure goes back like this. It's trying to come back. Yeah, the deformation here is big. It's gonna come back, but there will be some permanent deformation. We don't want our structures to do that. most of our structure, we need them to be in the elastic zone. So that's why we usually use this curve when we do structure analysis or even design. Everything has to be linearly elastic. So we'll find a note here. I'm saying if a bar behaves elastically, Hooke's law applies. And this Hooke's law, that means this relationship, the force and the delta, the relationship between them is linear. All right? Okay, so what if I want to find the work done by every one of these curves? Actually, the work is the area under the F delta or the B delta, like this area or this area or this area. Why is that? Because the thing is, the relationship between them is integration. If you guys remember the integration relationship, if you integrate B with D delta, so if B is the y-axis and delta is the x-axis, so the integration actually is the area under the curve. Why? Because basically the integration take a small piece like this, D delta, and multiply the D delta with the value F, so that's like a small triangle, and you integrate these pieces from 0 up to delta, so that's the integration. That's what integration do. So if you don't know, the integration relationship between two variables, the total value is the area under the curve between the two variables. Same thing here. If you got this area, so that's just gonna give you the work. If you got this area, that's just gonna give you the work. Same thing here. Like here is the same thing. You are gonna take a strip here, and this one is D delta, and this is the value F, and F actually is a function of delta, and you integrate this piece over the whole length, so from 0 to delta is gonna give you the work. So if this is triangle, so I can say that the work is equal to half multiplied by the base delta multiplied by the height F, so half F delta. If it's rectangle, so the work is gonna be equal to F multiplied by delta, because this is a rectangle. This one I can't, because that's like a complex curve, so I have to keep as integration from 0 to delta, and this is gonna be F d delta. I have to keep it that way, all right? Because I can't find the area of this curve. Okay, so based on this concept, let's actually start with trusses and see how we can apply the concept of work energy to trusses. So we're gonna cover trusses today, and next time we're gonna cover beams. Let's just start with trusses. Trusses is kind of like this bar. Like this bar, and I'm gonna take only one bar, and then we are gonna solve an example on multiple bars. But it's kind of the same concept. You have this bar is applied under load B. So this bar basically is gonna elongate, and let's say like this, and this is delta L, and this is the total length of the bar. So that's about the bar. So the strain energy inside this bar, we can describe it as U. We usually write the strain energy as U, and the external work we put W. So the strain energy basically is half F, the internal force, multiplied by the delta inside the inside this bar, which is equal to delta L. That is the strain energy.
F is the normal, right?
F is the tension inside the bar, and this is the internal force, the normal force inside the bar. Exactly. All right. So let's actually, I'll ask you something. When I pull this bar, the thickness or the diameter of the bar is gonna be less or more after it makes this deformation.
Less.
It's gonna be less, right? That's what we call a strain, right? It's gonna be longitudinal and okay. So the strain is equal to the deformation over delta L over L, right? This elongation over the total length L, that's the strain. Do you guys remember the Young's modulus is equal to stress sigma over strain? So basically I can say that the strain is equal to sigma over E. So right now I know what is the value of strain. Can you guys tell me if this part under force F, what is the value of the stress if the cross section is A?
The cross section is what?
Is A like the area, like if the area is equal to A?
F over A.
F over A. If F is the force and A is the area, that's the stress. So basically I can substitute with this here and I can substitute with this here. So I can say that delta L over L is equal to F over A and all this over E. So basically I can say that delta L is going to be equal to F L over EA. Do you guys have any issues with this rule? So I can then take this delta L and substitute it here. So I can say that the strain energy is equal to half F multiplied by F L over EA. That is the strain energy in a bar. All right? The second bar, let's actually see if this is a beam. What is going to happen? Let's say number 2, if this is a beam. All right, for a beam, it's a little bit complicated. If it's a beam, why? The thing is, we were lucky here that B and F are constant. Like B is a constant, and the internal forces here is constant. Like if you take a section here, the normal force is F. If you take a section here, the normal force is F. But for a beam, let's say that our beam is something like this. And it has a distributed load W. So I would ask you, what is the internal force that can make this beam has deformation like this? This beam is going to deform like this, right? What is the internal force that makes this deformation? I know that the internal force that makes this deformation is the normal force. But right now this beam doesn't have a normal force. It has a moment and has shear. So both these forces makes deformation, okay? But I'll tell you something, we're going to talk about it later. Most of the deformation in this beam is coming from the moment. 95% of the deformation is from the bending moment. The shear force is really, really low. That's why we sometimes neglect it. So that's why I'm going to focus on the bending moment, and we're going to come back to this beam later. Okay, so this beam actually have this deformation, and if you want to get the theta, it's basically dy dx at any point. So if you want to find what is the slope theta is, right? So that's something that we have learned from last time. If you guys remember, like if this beam, if I took a cross section here and I take this cross section outside, so basically this is what happens in the cross section. If this cross section is under a moment, it's going to have tension here, compression here, and this is, if you guys remember, d theta, and this is dx, and this is the neutral axis, and this is the origin, something like this. We did this before. So the problem with the beam is here, what is the value of the deformation here? And actually, let me put the bending moment as well, so that we can have both of them. If I want to write the bending moment of this beam, it's going to be something like this, and this is WL squared over 8. That's the bending moment, and it's positive. Look at this. Here, the deformation is constant, delta L, and force is constant. But here, if you get, this is delta, and it has different moment. Here, different delta and different moment. So the moment and the delta is keep it changing with the distance x. So right now, having one rule is not gonna work, and we have to do integration. So to do this, we take a small segment of the beam, like this segment, that has delta here, or that has d theta, because the thing is, right now I told you that the strain energy, we only are going to consider the one that comes from the moment. We're not going to consider the one that comes from the shear for now. So the strain energy is going to be half m multiplied by d theta, and that's not the strain energy. This is du, a small infinitesimal strain energy in this infinitesimal part. So if we want to find the whole strain energy in the beam, we have to integrate this part and integrate this part. Do you guys get that? So the only way that we can find the strain energy, we're going to take a small segment and try to look, how can we describe the strain energy in this segment? We need to find the theta before here and the theta after and get d theta and try to find the moment at this. So we are going to find what is the strain energy stored in this small segment. If we want to find the strain energy for the whole beam, we need to integrate from 0 up to the whole length of the beam. You guys got that? Okay, so the thing is, before I do this, I know that the moment is changing over x, right? Like, let's say the moment is keep changing, like this line here with x. So I want to convert, rather than d theta, I want to make it dx and integrate from 0 to L, right? This is much better. So I need to find a way to remove d theta and put dx. If you guys remember, d square y dx square equal to m over ei? The differential equation of the elastic line of the beam, and I told you don't ever forget it from the last couple lectures. And actually this is d theta dx, right? Because d theta is equal to dy dx. When you differentiate it one more time, it's gonna give you the second derivative of this. Theta is equal to dy dx. So if you differentiate it one more time, it's gonna give you the second derivative. So I can basically say that d theta dx is equal to m over ei. So d theta is equal to m over ei multiplied by dx, right? So I can remove d theta and put this. So this is going to be half m multiplied by m over ei dx. Okay? And since I have it ready, I can integrate both sides. Can integrate this and integrate this. So this is going to be integrated from 0 to L. And I can finally say that the strain energy in a beam is equal to the integration over the length of the beam. We can actually put 2 under. We're going to make this m squared over 2 ei dx. All right, you guys got that? And this is a really, really important rule when it comes to strain energy. So this is for truss, and this is for beams. And that makes sense, because trusses always have internal forces as a normal, so the normal force is F, and beams, most of the internal forces are moment, so this is the moment. By the way, when we do it for the shear, it's going to be the same thing. U is going to be equal to Q squared over, but not EI. It's going to be something related to the cross section and some other stuff here. Because here's EI and here's EA. Like, it depends. It's all about the stiffness that affects the internal force. But let's focus on just the bending moment for now. Well, this concept, we are going to use it next time, but this concept, we're going to use it today. As I said, today we're going to cover the trusses, but I have to give you a little bit of idea about the strain energy of the beams. So let's solve an example. For trusses. All right, so all what I need right now that you understand or that you memorize this, if you don't know how did I prove that, that's what I need from this, and that's what I need from that. And I need you to understand that the work is equal to half F multiplied by delta. That's all what I need from this 2 forces. This one, number 1, and number 2. This is for next time, but that's the tool that I need from you that to understand right now. Why? Because right now I'm gonna say that the external work is equal to the internal or the strain energy inside any structure. That's the rule that we are gonna use. So this work is gonna be equal to this energy. And next time, this work is gonna be equal to this amount of energy, right?
Very good.
Okay, so let's take these two and apply them for this example. So I have an example. This example is a truss, something like this. And I have a load equal to 30 kips kilopound here, and the dimensions are 15 foot here and 20 foot here. And I'm asking, using the method of real work. Oh yeah, this method is called real work. Okay, so I'm saying using the method. The thing is, the work energy method has two methods. One is called real work and one of them called virtual work. All what we are doing here is a real work. We are gonna learn the virtual work in a little bit. Okay, using the method of real work, determine delta x. I want you to tell me what is the amount of delta x that is going to happen here. And all bars are having same cross-section area, which is 2.4 inches squared, and the Young's modulus is 30,000 kips per square inch. Okay? All right, let's see how we can solve this problem. But before this, I want to ask you a question. If the force 30 kips is pushing that way, can you tell me how's the deformant shape of this truss look like? Definitely this point is going to move?
Right.
Right. Okay, I'm going to ask you, do you think it's going to be Y deformation or no? Just a little bit of deep thinking. If you push this bar, this has to be staying like this is going to move that way. Right? This bar is going to move that way. And since this is a roller, so this bar can be here. Right? So we are going to have something like this. All right? This point is going to move X and it's going to move Y. Definitely the displacement is going to be small. I'm just making it bigger so that you guys can imagine what's the displacement. However, with the method of real work, I will only be able to get the displacement delta X. I can't get the displacement delta Y with the method of real work. I have to use another method, it's called virtual work, to find it. Because the thing is, I will be only able to get displacement in the direction of the force. I will not be able to get a displacement that is not in the direction of the force. The method of real work is not going to happen. Why? Because the thing is, the whole method is based on the B multiplied by the delta in the direction of the force. So any delta is not in the direction of the force, I cannot get it. I have to find another method to get it. So let's find out how we can get delta X. And that's why I asked you the question, find delta X only, don't find delta Y. But you have to know that there is delta Y. So the first thing to solve this truss is to find the reaction in the original system. Can we do that? All right, I'm gonna put the truss. Actually, let's find the reaction of the same system. Let me ask you, is it easy? The thing is, there's no vertical loads. All the loads are horizontal. Can you tell me where's the horizontal reaction? It's gonna be here, right? At the support. This one cannot take any horizontal reaction. So I'm gonna have a 30 kips going that way, right? To resist this 30 kips. The 30 with the 30 is gonna make a couple, right? These posts wanna make a couple that way. So definitely I know that the reactions that need to develop here need to make a counter couple that is gonna counter this force. So I know that there will be a reaction here and a reaction here to make a counter couple that way. And this couple is equal to 30 multiplied by 20. By the way, I'm making it in a way that is not much faster for me, but in the exam you have to do summation of x. You get the moment here, you get the reaction here, you get the moment here, you get the reaction here. But I'm telling you other ways that you can get the reaction faster. But in the exam, I want you to get the summation of the moment here, you get this reaction. The summation of the moment here, you get this reaction. So what I'm saying is 30 multiplied by 20 is gonna give you 600, that's the couple, that's the moment. 600 kips foot, all right? So this is gonna be 600 over 15, and once you make this division, it's gonna give you 40 kips. So I know that this is gonna be 40 kips, and this is gonna be 40 kips. If you wanna make sure that my answer is right, take the moment here. 30 multiplied by 20 is gonna be equal to 40 multiplied by 15. If you wanna do it from here and get this one, so you are gonna have 40 multiplied by 15 is equal to 30 multiplied by 20. All right? Okay, that's one way to do it. So I got the reactions. If I got the reactions, I can get what is the internal forces in the trusses. So basically, this one is very easy because I can know that this truss is under compression and this compression is negative 30 because this 30 need a compression that way to resist the 30. And I can know that this one also is under compression and this compression is negative 40. That's easy, members. If you don't know what I did, you cut here and take this joint and do some Fx, some Fy, and try to find the forces in each member. Same thing, you have to do it here. This is a little bit difficult because it has an inclined member. So you have to assume that the force in this member F, and there's F cosine theta and F sine theta, and try to find the value. But I know for sure that this member is under tension because this one got bowled away. So I know that this one is under tension, and once you solve it, you are gonna find that this is equal to plus 50. Yes, double check. Yeah, it's plus 50. If you don't know how to do it, you cut this that way. This is the force, it's compression. I already found it, and it's equal to 30. And this member is gonna have a force F that I don't know. And I know the theta here because the sine theta is equal to 15 over, can you guys find this member? 15, 20, this is gonna be 25. So cosine theta is gonna be 15 over 25, and sine theta is gonna be equal to 20 over 25. So I have F, so the component of F here, you're gonna have F sine theta, and you're gonna have here F cosine theta. So you have the reaction here is 40, so F sine theta is going to be equal to 40. So F multiplied by 20 over 25 equal to 40. So you can find the value of F is going to be equal to 50. That's the way to get it. You were supposed to know how to get this stuff because the first structure analysis class was about trusses, to solve trusses. That's the basic one. Anyway, so let's assume you found the reaction and you found the internal forces. What I'm going to do next, I'm going to apply the concept of work and energy, that the work W, the external work, is equal to the internal strain energy. The external work comes from the external forces. How many external forces that I have on this structure? Just one, that's 30, right? So 30 half B multiplied by delta is gonna be equal to, that's the force, that's the external force, half B multiplied by delta, is equal to half F multiplied by FL over EA. That is the strain energy, that is the external force. So half 30 multiplied by the displacement that this 30 make, delta x, that I don't know, equal to half multiplied by the force multiplied by this element. But the thing is, I have 3 members, so I have to do the same procedures for all the 3 members. So it's going to be F squared multiplied by the L of the member over EA. Since EA is constant for all of them, so basically I can say half multiplied by, and I can put E, which is 30,000, multiplied by A, which is 24. And pay attention to the units. These are inches, and the lenses are in feet. So we need to convert one of them. I'm going to convert the lenses. I'm going to keep the E in inch and the A in inch. I'm going to put them down there. And then I'm going to take F squared L for each one of them. So each member, this member has negative 40, this member has negative 30, this member has positive 50. It doesn't matter if it has tension or compression. Why? Because it's going to be squared. So the sign, positive or negative, is going to be gone. So I'm going to have 40 squared multiplied by the length of this member, which is 20, plus 30 squared multiplied by 15, plus 50 squared multiplied by 25, and all of these is going to be multiplied by 12. Can you guys tell me why?
Inch.
To convert what?
The lengths.
To convert the length, so I take the 12 common factors, so the 12 is going to multiply by 20, multiplied by 15, multiplied by 25.
So it's a sum of the forces.
Yeah, the sum of all of them. So I have to put this as the sum of all of them, all the forces. If here it was only one member, right now we have 3 members, so this external forces, this external force made strain energy in all the members of the truss. So we need to find the summation of all this strain energy, and it's supposed to be equal to the external work done on the truss. So solving this is one equation and one unknown. You will find that delta x is equal to 0.6 inch. So the general rule that we have here is the half the force B multiplied by delta is equal to the summation of all the strain energy in all the truss member, which is half F squared multiplied by L over EA. That is the concept of work and energy. All right? And this concept only applies if you want to find displacement in the same direction of the external force. But if you want to find other displacement, this is not going to work. Okay, let's see how we can apply this to get other displacement. Thank you. Does anybody have any questions so far?
Why do we use half force times delta instead of just force times delta?
Because the thing is, most of our structural members are behaving elastically, and that's what I said. I don't know. Have it here. So this is how most of our structural members. You put the force in gradually, and the force is increasing linearly with the displacement. However, if you have it like this, it's fine. You are gonna put, if I told you that it's gonna behave that way, so you're gonna put F delta. And at the end of the day, if it behaves like this, you're gonna have half here and half here are gonna slash each other. So at the end of the day, it's gonna be the same concept. All right? Because you have over 2 here and over 2 in the strain energy. So if they are not linearly and the force is constant, so there will not be half in the work and there's not be half in the strain energy.
Okay.
All right. So. All right, I need you to focus here because we're gonna do some serious stuff. The method that we're gonna learn right now is called virtual work. Virtual as we said, one of the limitations of the method of real work is that it doesn't allow us to find the deformations in other places. What if I want to find this deformation? What if I want to find this deformation that happened in this member? I can't find it with this method because this method, B has to be in the same direction of the delta. But with this method, this delta, I can get it, and it's there. It's not equal to 0. And there's delta here, it's there, but I can't get it using this method. So let's find how we can find this. First, I have to explain something. Let me put it here, actually. I'm gonna put it here. So I'm gonna put a truss member like this, and I'm gonna write the same one. And the same one here. So these are the same truss member, or the same bar, and I'm gonna put different loads on them. So, and the boundary conditions of these bars are like there's a hinge here, and there's a roller here. So basically this point is attached, can't move, but this roller can move in the X direction. And let's say I'm gonna put, the load that I'm gonna put here is the actual load on the beam. The actual load on this beam, let's say, this, I'm gonna say it's B. That's a load B. That's the real load, okay? And I'm gonna put a virtual load Q on this one, same beam. But this load Q is way smaller than B, maybe 1 ton or something. And here, I'm gonna apply both loads. I'm gonna put Q first, and after I put Q, I'm gonna put B, both of them together. So let's see how each one of these members are gonna behave. That is my actual system. The actual system in real life has a real load B. So basically, this point I can imagine is gonna move a little bit that way. So this member, under tension or compression? Tension, right? Why? Because if I want to find the actual deformation, by the way, this is delta. This is the external displacement that happened because of this load. Let's say it's delta B. But the internal deformation inside the member is this, right? Because that's how much the member elongated. And let's say that this is called delta LB. So we're gonna leave it for now. So that's delta B. How about Q? Same concept. This member is gonna come here, and this is actually is gonna be delta Q, and this is the internal deformation, which is delta LQ. For B and Q together, I believe that this is gonna be much bigger deformation here, and we are gonna have delta total, and this one is the delta L total. And with my engineering sense, delta total is going to be equal to delta Q plus delta B, right? And this one, delta LQ, is going to be delta LB and delta LQ, if you want to find delta L total. However, let's draw the relationship between the force and the displacement. Like if I want to look at the work, so first I'm gonna look at the external force. Here I'm gonna look at the work. Here I'm gonna look at the strain energy, all right? So let me use the symbols that I have here. F. All right. So I said that the internal force inside this member is I'm gonna describe it by F, and the external force I'm gonna describe it by B. So if I'm gonna look at the work is done by external force B. So basically the relationship between B and delta is gonna be something like this. I'm gonna have B here, and B is responsible of external displacement, delta B. I want you guys to differentiate between external displacement and internal deformation, right? external displacement, this is external displacement. This is a deformation inside the member. So if I want to put the deformation inside the member, it's going to also be something like this, but this is happening because of a force inside this member that is tension, and the value of this force is F, which is totally different from the B, and the deformation inside the member is equal to delta LB. I'm going to call all these B, because this is B means coming from the original load. How about the virtual load Q? For the virtual load Q, you are gonna have, by the way, right now, this Q is the main load, is the external load. So I'm assuming that this load is something like this Q, and this load is responsible of delta Q. And this load make an internal force inside this member equal to F Q, and the deformation is equal to delta LQ. Are we all agree on that? Okay, what if we put the two loads together? What is gonna happen? All right, let's track. First, you are gonna have Q, so Q is gonna go something like this. And once you finish all the Q, you are gonna go up and add the B, right? So you put the Q, and once you finish the Q load, you put the B load. So Q is gonna be responsible of this part, delta Q. And then once you put B, it's gonna be responsible of the next part, which is delta B, and both of them together is the delta total. All right? Same thing when we look at the energy. The energy you are gonna have here, once you put Q, Q is gonna generate FQ until you come here. And then once you push the B, B is gonna generate, and it goes up to FB. By the way, when I say here FB, that means this part, from here to here. So the total value here is gonna be FB plus FQ, right? Okay, so, and the deformation that we're gonna have here is delta, sorry, it's the delta, the other one, delta LQ, and this is delta LB. All right. So let's look at the work and the energy here. I know that the work is the area under this curve, and the energy is the area under this curve. So I want to find, this is W, and this is strain energy. So if you want to find W, B is going to be equal to half B multiplied by delta B. If you want to find the strain energy from B, that means coming from the original load, B, is going to be equal to half multiplied by FB delta LB, and they are equal to each other. Why? Because the concept of work and energy. The work is equal to the strain energy. Same thing here. We're gonna call this W, not Q. I'm gonna call it WD. If you wanna call it WQ, that's fine. And this is UD. So WD, same concept, is gonna be equal to half multiplied by Q multiplied by delta Q. The strain energy D is gonna be equal to half multiplied by FQ, and this is delta LQ, and they are both equal to each other, right? We agree on this. So the thing is, these are completely different systems. To be honest, this one is the system that I'm interested in, because that's actually the actual load on the beam. This is actually the virtual system, doesn't exist, with a virtual load, which is Q. I want to relate my virtual system to the original system, so that's why I had to push the two forces together to find a relationship between each other. So that's why I pushed the Q and then I pushed B after to find relationship between them. So look at this one. What do you think about these two triangles? The area of these two triangles, they equal to each other, right? This triangle equal to this triangle because it comes from these two. And the same thing, this triangle and this triangle. This is WB and this is UB. And this is WD and this is UD. The thing is, the area under the big triangle should be equal to the area under the big triangle here. So we can find out from here that definitely the area under this square is equal to the area under this square. Does anybody have any problem with that? Because the thing is, this is equal to that, and this is equal to that, so the rest amount of the area here is gonna be equal to the rest amount of the area here. Can you guys find what is the area of these rectangles?
SP times Q.
Huh?
Delta B.
Delta B times Q, right? So Q times delta B is gonna be equal to
The area. Oh.
Hmm.
FQ
FQ
times delta LP.
delta LB, right? So right now we found a relationship between the virtual load and the displacement that comes from the original load, delta B. So if you put a virtual load on a beam or a truss, the amount of virtual load multiplied by the displacement generated from the original load is equal to the internal force from the virtual load multiplied by the displacement that comes, the internal forces in the original load. Okay, so that is the general rule that we have. However, we found delta LB somewhere here. Delta L is here. F L, right? So basically, I can write this for trusses. Q multiplied by delta B is equal to FQ multiplied by
FL over EA.
F L over EA. This F here is the internal force that comes from the original load, which is FB, not the FQ, because that's the one, because delta B is coming from the original load,
Right.
so FB coming from the original load, and L is the length of the member, E, since this is B, this is gonna be B. So that is our rule for now. That's the one that we are gonna use, and that is the rule of the virtual work. And this is only for one truss member, right? What if we have for trusses that has multiple members? The rule is gonna be something like this. Q multiplied by delta B is gonna be equal to the summation of FQ, put it DR, okay, we can keep it like this, and this is FBL over EA, and that is gonna be the rule if you have a big truss. So let's actually see how this can be applied in real life if we have a problem. So why did I do all that? So I can come up with this rule. I want to connect a virtual system with a real system. And this concept is called the concept of virtual work. By the way, usually when we solve any structure, we put Q equal to 1. And we call this as the virtual load. Why we do this? So that Q can be gone. And only the delta B is equal to this value. And FQ is resulting from point 1 unit load at the point of interest. Okay, I'm gonna put it back here so that you can put 10, you can put 100, but the more load you are gonna put, the more complicated you are gonna make. So basically, the limitation that we have from the method of real work that we cannot find the displacement here, we basically put a unit load in the direction of the displacement that we wanna find. And then we can find the displacement that we want to get. Let's actually solve the problem and see how it works. Maybe we don't have much time, but I'm gonna try to cover as much as I can. Maybe we continue next time.
Can't even see the borders.
Okay, I'm gonna put here the general equation of virtual work. The general equation of virtual work. Delta at any point is equal to the summation of FQ, FB, L over EA. But this is under one condition. Do you know what is the condition? We just talked about it right now. This is assuming that the virtual load is equal to 1. So how we can solve any virtual load? any virtual load problem, basically, if I ask you the displacement in a specific direction, you put 1 unit load in this direction, and then you solve the whole problem. Let's find out. So, but before I do this, the thing is, if you have a big truss, and this truss is every member has FP and FQ different, and the L's are different, and maybe the inertias are different. So we usually make a table like this. And in this table, you put the member, like member AB, member BC, and then you go all the way down until you finish all the members of the truss. And then you put the FQ on each member, the FB on each member, and the length and the EA. If E is different and A is different, you make them separate. And then at the end, you get the value of FQ, FB multiplied by L over EA from this line. So you finish member 1, you find member 2, and at the end, you get the summation of this column. So usually, using Excel sheet, if it's a big truss, is much better. But in the exam, I'm not going to give you a lot of members. I'm going to give you just a handful of them. Okay? All right, so this is how we plan solving these structures. Okay, so let's actually make a truss similar to this truss, but less members. So I'm gonna have a truss like this, and I'm gonna have here hinge, and this is and there's a load here equal to 30 kips. And I'm asking you using virtual work compute the component of displacement at B. Calculate delta at B, which has delta X and delta Y. I give to you that the area is equal to 2 inches square, and the youngest modulus is 30,000 kips per square inch. So it's only one rule that we have, the summation of the Q delta B is equal to the summation of FQ FB L over E A. All right, so if this member is under this load, so I assume that this, by the way, this is hinge, so basically the hinge is not gonna move. So I assume that this point is gonna come here, and this point is gonna be something like this. So this is gonna be, you're gonna have delta X, and you are gonna have delta Y. That's what we need to find out. To solve this problem, first you have to find the reactions and the internal forces in the original system. Why? Because our equation has FP. FP is the internal forces from the original system. FQ is coming from the virtual system. All right, so let's find the original system. You'll tell me, but this is indeterminate. I have 4 reactions, but I will tell you something. The thing is, this one is not going to have X reactions because there is no members that can balance this X reaction. Since this member is inclined, I can assume that there's the X reaction is here, so I can have the 30 kips here. You'll tell me, why not here? Because the thing is, if you have a reaction here, X and Y, there's only one member here. It cannot balance this member. Here is the only way to take this X reaction because this is going to have 2 components. This member has an X and has an Y, can balance this reaction. So for sure, this 30 is going to be resisted by this member, by this inclined member. And that makes sense. Like if you have a member like this and you have a 30 load like this hinge cannot do anything with this 30. It's going to flip. It's going to rotate like this. The only way to resist this 30 is to pull it with something, another member like that. So that is going to take the whole 30. And using similar concept like the one that we did here, these two is going to make a moment like this, so I can assume these are going to have a counter loads of 40 kips and 40 kips. In the exam, you have to do it with the original way. You get the moment here, you find the reaction here. Get the moment here, you find the reaction here. Or you use Fy, summation Fy equal to 0, 40 is gonna cancel the 40. Okay, I got reactions. If you wanna find the internal forces, basically this is 40, this is gonna be under compression, so I can assume that this is negative 40. This is gonna be under tension. You try to take the joint out and try to find the force in this member. And when you solve it, you're gonna find out that this is positive 50. So what I did right now, I solved the original system. I solved the FB, the internal forces in the original system. How about the virtual system? Since you need delta X, I'm gonna draw this stress 2 times. One like this, and one like this. And I'm gonna put all the internal support, I mean like the external boundary conditions. And the thing is, when we solve the virtual system, we take all the original loads. We took this original load out, the same way that we did here. We take P and we put a new load, it's called the virtual load. And I told you this virtual load is better to be 1 unit load, so it can make your problem easier. If you put it 10, it's okay. If you put it 100, it's fine. But 1 is much better. If I ask you about delta X at this point, you put unit load at this point is equal to 1. If I ask you to get delta Y at this point, you put unit load at this point equal to 1. If I ask you about delta here, you put unit load at the delta that you are interested in. Okay? So there is virtual system 1 and this is virtual system 2. What should I do next? You find the reaction and the internal forces from this load. So once you solve this, you're gonna find out that this is equal to 1 kips, and you are gonna find out that this is reaction here, and these reactions are 4/3, and 4/3, and this is gonna be under compression, and this compression is negative 4/3, and this one is gonna be positive 5/3 tension. This member is gonna be, I'm gonna have only 1 kips reaction here. This is gonna be 0. And you will find that this member is under compression equal to 1. Solving these trusses like normal trusses did. Okay? Almost done. Alright, let's apply the rule. Very simple, very easy. Rule number 1. Q delta X is going to be equal to the summation of FQ, FB, L over EA. So Q is equal to 1, and I'm only interested in delta X, so 1 multiplied by delta X, the one that I'm interested in, is going to be equal to the summation of Alright, this member, FQ is equal to negative 4/3 and FB is equal to negative 40. So I'm gonna say negative 4/3 multiplied by negative 40 multiplied by L negative 40 multiplied by L, which is 16 foot, plus this member is 50 and 5/3, both are positive, so 5/3 multiplied by 50, and the length of this member, the root square of 12 plus 16 is 20. The length of the horizontal member is 20, yeah. And all this is divided by EA. So when you divide this over EA is gonna be 2. By the way, I forgot something, but you guys are gonna tell me what it is. What did I forget in this equation? The what? Times 12, yeah, the conversion from feet to inches. Okay, and then you're gonna find the value of delta X. It's gonna be equal to 0.5 inch. Same thing with delta Y. You're gonna say 1 multiplied by delta Y is gonna be equal to, and you put all this, It's only one member. 1 multiplied by 50.
No.
So we're gonna,
1 multiplied by 40, right?
oh, sorry, 1 multiplied by 40. And this is not positive, this is negative, so it's conversion. So, -1 multiplied by 40, multiplied by the length, which is 16, multiplied by 12, which for the conversion, and this all is over 2 multiplied by 30,000. So delta y comes from this is gonna be equal to 0.128 inches. If I ask you about the delta at any point, it's the same concept. You put 1 unit load and you get the virtual system, you have the main system, and then do the equation together. Do you guys get that?
Yeah.
Okay, we're gonna apply this rule many times. Next time we're gonna practice more on trusses, and we are gonna practice more on beams, and you are gonna understand what is the virtual system is, and what is the main system, and how you can do the analysis together. See you guys next time.
Thank you.
Thank you.